Welcome to this presentation of flood forecasting in Norway. My name is Elin Langsholt and I have been working with flood forecasting for about 20 years. NVE, that means Norwegian Water Resources and Energy Directorate, has been in charge of the National Flood Forecasting Service since 1989. It was built up and came into operation after a severe flood in October 1987. Then we started out with flood forecasting, but warning services for landslides, for snow avalanches, and large rock slides have come into operation later on. In this presentation, we will go through some different things. We will look into the motivation for running this warning service, and we will have a look at how it is organized. Then we will go into the different kinds of floods, as floods differ according to what flood generating process is behind and which time scale we do think about. Then how do we do the flood forecasting? What kind of data and models do we use? And we will look into the important issue of getting the message out, the communication with the people and emergency authorities out there who are the ones that are actually affected by the flood. Early warnings are meant to alert about potentially hazardous hydrological situations and first of all floods. Floods are expensive and we want to reduce losses. And then we need sufficient time. To reduce losses can mean on the short term to clean up drainage systems or to remove camping vehicles, boats and so on from exposed areas. Or on the long term to try to prevent situations that can increase the probability for flood, like in the spring season, to have a good communication with the hydropower companies so that all parts are aware of this year's situations. When it comes to things like snow storage and reservoir fillings, for instance. Then when the flood is there, there's a big need for information about the situation and the forecast for the coming days. And private persons, communities and media are all very eager to get that information. And the flood forecasting service wants to give that information, and we want all in all that the society's awareness towards floods increases. We are a handful of people taking part in our warning services, and 14 of us take part in the flood forecasting duty, taking 1 week each, and we are always 2 on duty. The duty goes from 8 to 9 p.m. and can be quite busy if there's a flood going on. The working day always starts with a chat with the meteorologist. The weather is of course very decisive for the risk of flood. The daily routine goes like this. We take a look at the state, observations, things that can affect the flood risk. Is the stream flow high? Is it wet in the ground? And so on. Then we consider the weather forecast. We take a look at the precipitation and temperature data, and very often the meteorologist in the chat gives some adjustments according to his or her interpretation of the model forecast. The Met forecast is input data to the hydrological models, which compute the hydrological forecast. And then if the hydrological forecast indicates flood at some level, we will probably have a busy day with publications of flood warnings and communication with involved parts. Floods appear in different scales in space and time, much according to season and climate. Summer is high season for heavy showers, which may particularly give big problems in cities because of deficiencies in the urban drainage system. But also in more rural places, heavy showers can make much damage when small creeks grow to big rivers and can find new routes through the terrain. And riverbeds can be unstable and give rise to flood slides with loads of sand and boulders. Prevailing rains for several days can make large floods in big rivers, and in regions with snowy winters, half or so of the yearly precipitation melts within just a few weeks in the spring and can make a snow melt flood. And accordingly, the different flood types are generated by different weather types. The heavy rain showers make urban floods and flash floods. When the showers are of a larger scale and more in the form of intense rainy weather, they may give rise to rain floods, first in the smaller rivers, but as the rainy weather lasts for a longer period, the bigger rivers may be flooding as well. The snow melt flood is caused by the nice weather called spring, when high temperatures, typically over larger regions, lasting for several days or weeks, can build up large-scale floods in the big river and lake systems. Then, when heavy rains coincides with warm melting periods, the spring flood can be really disastrous. And these flood-generating processes are characterized by different time scales. In cities, just a few minutes is enough to make small lakes in poorly drained paved roads. It takes some hours or so to build up a flash flood or flood slides in more permeable rural terrain. A capable rain flood in fairly big rivers takes some days to accumulate. And the big river spring flood is the result of a couple of weeks or so of snow melting. But within these rough classes of floods, there are many other factors that can affect the nature of the flood. In steep terrain, everything goes fast and the river responds very quickly to a rainfall, if the ground is wet then. If you have regulations in the catchment, you may not have response at all because the rain is caught up by an upstream reservoir. If there is capacity in the reservoir then. This is often a nice factor in the spring when many reservoirs are well drained after a dry, cold, energy-consuming winter and have plenty of space for a good dash of melting water and thus contributes to a less dramatic spring flood. But even unregulated lakes have a dampening effect on floods, increasing the water's retention time in the catchment. And the same effect is seen in catchment with a high portion of bog. Vegetation and evapotranspiration also play a significant role for the response to heavy rainfall. A lush green vegetation cover consumes considerable amounts of incoming water and less water is released to the rivers. So there is a lot of factors to take into account, and we have models that are constructed to take care of this. The models are forced by observed weather data, that is precipitation and temperature in our system. The data are presented at cnorge.no and is a 1 by 1 square kilometer distributed dataset, where all available observations are interpolated to a grid scale. This updates the model's internal states, which is the starting point for the hydrological response in the forecast period. The Met Office serves us with the weather forecast. The forecast has its origin in the global ECMWF model, which gives a long-term forecast, that means 10 days. And it provides initial and boundary conditions to the regional scale model that makes a more high precision weather forecast for the first 3 days. Some processing, downscaling, and bias correction is needed to tune the forecast and to transfer the data to the Se-Norge grid format, which is the model input data format. Given the weather forecast input data, the hydrological models compute the hydrological forecast, which may include a flood if the weather conditions are very wet or very warm. The HBV model is our good old workhorse, and it is a traditional rainfall runoff model. It is a conceptual model where different types of storages together represent the river system. A snow storage estimates accumulation and melting of the snow, and this is a very important part of the model since a big part of the annual precipitation may fall as snow, and the melting of it typically results in a big flood. In the soil storage, evapotranspiration is computed and much of the model response is determined. In the dynamic part of the model, the response discharge is computed. At present, we run the model for 3 hourly and daily time steps. For flood forecasting, it is first of all the catchment models that give useful information. We run models for 147 discharge stations, together representing most kinds of terrain, climate zones, and catchment sizes in Norway. The catchment is distributed into 10 altitude zones to be able to represent snow accumulation in a good way. There is a distributed version of the model operating as well, and this model computes the countrywide water balance and gives daily snapshots of the hydrological states, snow storage, soil moisture, groundwater storage, and evapotranspiration. Two other model concepts that we use for flood forecasting are the DDD model. It is developed in NVE and it needs practically no calibration because the model parameters are physically based and we can find them from a map. And this is a big advantage in ungauged catchments. We also run a bundle of data-driven models, and this is a purely statistical approach and is also called machine learning. Looking at the flood scale slide again, we can see that the weather forecasts appear in different scales as well. To be able to catch the flash floods and the urban floods, one needs to use the nowcasting, where radar images are extrapolated 90 minutes ahead with the use of weather model fields and available observations. The regional scale weather model, forecasting 66 hours ahead, give high precision weather forecasts that is good input for forecasting rain floods. And the long-term weather forecasts can see more than a week ahead, although the uncertainty that far out can be quite big. Then it is possible to follow the development of larger scale rain floods and snow melt floods. Before the snow melt season, we use extended weather forecasts that goes 6 weeks ahead and historical weather as input to the hydrological models to say something about the probability of a large spring flood. The severity of the expected flood is expressed by the warning level. The green level is the normal situation and no warnings are published. A warning has a yellow, an orange or red level, and that is a quite international standard. The yellow level means, as a rule of thumb, stream flow exceeding the mean flood. The level also includes local flooding after heavy rains, seasonally large stream flow, and risk of ice drift situations. The orange level indicates stream flow between the 5 and the 50-year flood, and that means extensive flooding and probably local damages. At red levels, we may have a disaster with severe flooding and heavy damages. A couple of new needs have shown up the last years. Warnings of flash floods or urban flooding caused by intense local showers are now issued by the Met Office, since this is a Met phenomenon more than a hydrological one, and have its own little baby boot. And drought situations are illustrated by this desert sandal. We have a constant ambition to improve the flood forecasting service, both the precision of the warnings and the communication with the public. There are a few things we can list up that are critical for a good flood forecast. First, observations. The hydrological data are the core of the service. These are the result of the observations on our few hundred streamflow stations and the never-ending job of looking after the stations, quality checking the data, and making discharge measurements to get a better rating curve. The weather forecast is crucial. The stream flow condition is completely determined by how the weather turns out. To interpret the weather forecasts is an art in itself. The regional scale and the global scale forecasts give different information that apply differently. And ensemble forecasts are very useful to quantify the uncertainty in the forecast. Hydrological models are important decision support tools, but there's always a significant uncertainty associated with the hydrological models. Models are very simplified representations of nature. They are usually calibrated on streamflow only, leaving snow and subsurface processes living their own lives. And there may show up situations that the models are poorly trained for. So model results should always be regarded with a big portion of skepticism. And here the human touch comes in. The overall interpretation of the data and the model results is what eventually manifests as a hydrological forecast and maybe a flood warning. Not least the communication of the warnings to the public and the emergency authorities out there is decisive for the flood warning to have the desired effect of preparedness and increased consciousness towards such hazards. And good flood forecasts will be needed in the time to come. Effects of climate change will be more intense rain showers, more rain floods in the autumn, and more winter flooding. And this is a good motivation to keep on improving the flood forecasting service. And here I end my presentation of flood forecasting, and I would like to thank you for your attention.